Hello, everyone. Welcome back. Now we are ready to listen to Walter Brown with the lightning strikes. Enjoy.
Thank you very much. Hello, everyone. I'm speaking to you from near Chicago, Illinois, in the United States. So I wish you everybody a good morning, because here it is 8 o'clock and we are ready for breakfast. Before we get underway with the talk, I would like to take a moment to say a special thank you to someone special. As some of you perhaps know, ever since I retired, I have tried very hard to acknowledge someone who has been very, very important to my life for a very long time, and that would be my wife. And as some of you may know, over the years, she has made for me a number of ties that I often wear when I give talks at conferences. I'm at home, so I'm not wearing a tie today, but here is a recent tie that she made for me. I don't know if you can see all the details, but you'll notice the pattern is all zeros and ones. It's a binary tie. And most recently, about 8 weeks ago, in the midst of the current pandemic, she made for me, from the same fabric, a mask, which I refer to, of course, as my bit mask. I may be the only person in the world who has a matching set of tie and mask. So thank you to my wife. All right, let's get underway. Lightning strikes. As I'm sure many of you are aware, lightning talk is usually defined as a very short presentation given at a conference or forum that is similar. But it is claimed that the term was first coined in June of 2000, although it is said that the practice of lightning talks was first known to be used in 1997. Well, I beg to differ, because I remember from almost 50 years ago, at the first programmers conference I ever attended, we had an hour of short talks with a common title, What Every Fortran Programmer Ought to Know. You can tell that's an old title because Fortran is still spelled with all capital letters. We haven't done that for several decades now. So that talk in 1971 was memorable, at least for me, in part because not every topic needs a full hour to talk about. So what I have for you today are several mini talks in the approximate style that I saw, as I say, roughly 50 years ago, but this time with C++ as the unifying theme. So as the overall title, since this is an homage, I first thought of calling it What Every Fortran Programmer Ought to Know. Oh, wait, no, I meant C++. Yes, of course, what every C++ programmer ought to know. But that seemed too grandiose, too obvious, too much like a clone. So I chose the simpler lightning strikes. Lightning, of course, referring to lightning talks. And what I have for you today are 4 topics. Why are they named Lambdas in C++? Then I'll talk about some of the underlying principles of C++ declarations. I'll talk about the universe of C++ types and how to classify them. And I want to conclude with a brief recap of the life of a 20th century mathematician whose influence on C++20 has been considerable and yet largely unacknowledged. So with that, let's get started with why are they named Lambdas? There are a number of pioneers of computation whose names are well known and some whose names are less well known. But those of us who do computing should be aware of these people and their respective contributions. Here are 5. Here are a few more. Andrei Markov is the son of another Andrei Markov whose work you may have heard of as Markov chains. Well, this is his son, Axel Thue, Bertrand Russell, Alfred Whitehead, and Dana Scott. the only one of these 10 who is still living. And of course, there are others. What they have in common is that they were early researchers of what they then called the foundations of mathematics. And over time, their respective works converged, for the most part, into a branch of mathematics that is today known as computability theory. Church's notation in particular became the foundation of the programming language Lisp, which I believe is still the second oldest programming language in continuous use. Fortran, I think, was first by about a year. Lisp, I believe, was second. I'm fond of this particular quote, however, speaking of Lisp. It's today's equivalent of Latin, because educated people are supposed to have studied it and forgotten it. Peter Demoff wrote that in a paper about 5 years ago. Functional programming, as practiced in Lisp, as most of us know, lives on. And in that kind of a discipline, functions are not only callable, but are treated as copyable values as well. And in C++, function objects have always fit this description. So in C++ 11, we introduced Lambda expressions as a concise way to create a simple function object. Here's the citation. That's a quote from the C++ standard, in case anyone cares to look it up. Of course, C++ lambdas have evolved with every C++ standard since. We have relaxed restrictions. We have added facilities. Most recently, C++ 20. Lambdas can now be templates. Interesting feature. But there are some who believe that the original untyped lambda calculus was the first object-oriented language, from a talk given in 2009. So where did we get lambda as a term of art? Well, today, routinely, math functions are named. We say f of y, where f is the name of the function, as in this example. And as best I can determine, Leonhard Euler was the first to do so in 1734. But in his work in the 1930s, Alonzo Church used anonymous function definitions in his work in computing foundations. In particular, he wrote y hat dot 3y plus 1 as an example of an anonymous function of y. Now, he didn't originate that notation. He adapted it from earlier notation used by Whitehead and Russell. They used it for class abstraction. Church adapted it for use as a form of function abstraction. And by the way, the hat notation is the form that I was taught, I believe, in my first term of graduate school. In 1964, Church wrote about his choice of notation. He said that when he published his work, again, mid-1930s, the caret, or hat, was typeset not above, but separately, alongside the variable. And of course, when it's there and larger, it looks like a Greek capital lambda. And then later, editors changed it to lowercase, thinking it looks better. And that's the origin of the term lambda. Well, maybe. Dana Scott, who was a former student of Church and was one of the early Turing Award recipients, gave a talk in 2018, and he told a different story. He said during that talk, which you can find online, that he once talked to Church's son-in-law whose name is John Addison, asking him to talk to Church, his father-in-law, about the origin of lambda. So in fact, Addison did write to Church. He sent him a postcard asking, why did you choose lambda as your operator? The story continues. Church returned the postcard in an envelope and had written on the postcard the phrase, eeny, meeny, miny, mo, suggesting it was a random choice. So we now have two different stories from Church. I'm not sure which one is true. So whether we believe that the choice was typographical or arbitrary, there is no doubt about the fact that this notation for functions and function abstraction became known as lambda expressions. The collected work that Church did in this area became known as the lambda calculus, and that's what I was taught, as I say, as an early graduate student. It has long since been regarded as a universal model of computation, and it's been proven equivalent in computational power to the models that others produced, in particular post-Kleene and Turing. By the way, two of those three were also graduate students of Church's. It is not particularly well known, but Stephen Kleene, whose work we use every time we do regular expressions, because he was the first to use the star in a regular expression, and it's referred to in certain circles as the Kleene star or sometimes as the Kleene closure. Turing also took his doctorate under Church, I believe, in 1936 to 1938. Nonetheless, why are they named lambdas? We now know two stories why. So thank you for your attention. Let's move on to the next mini talk. Underlying principles of C++ declaration syntax. This is the most succinct statement that I could find by Dennis Ritchie. For those of you who may not recognize the name, Dennis Ritchie is the originator of the C programming language. And when he gave this talk in 1993, he said, quote, "The style used in expressions carries through to declarations." I knew Dennis Ritchie a little bit, not particularly well, but we interacted at some conferences. Now, it turns out that we kept that principle in C++, and let's look at some specific examples, and questions, and then answers. Let's say that we want some entity X. What expression involving X could give me a result of, say, type int? Well, if it's a simple variable, I just write X. If it's an array, I would write X with some subscript in brackets. If it's a pointer, I use the unary asterisk to dereference the pointer. If it's a function, I call the function with suitable arguments. So for each of those four cases, how would I declare X to get that effect? It's a simple variable, I just say int X. If it's an array, I say int X with a number in brackets. If it's a pointer, I say int star X. And if it's a function, I say int X with a suitable parameter list. In other words, the expression that I would use to get a value of type int finds a mirror in the declaration of the entity that I want to use. So in general, a declaration starts with a type, and it's followed by an expression known in this context as a declarator. And that expression would be of a form that can give a value of the type we started with. And then there's punctuation, a semicolon if we're finished. Otherwise, we can have a comma and keep going. And we see, these are the same examples from the previous page, that in fact, in every case, that's precisely what we have done. We start with a type, followed by a declarator, and then punctuation. It's important to realize that in declarators, precedence still applies. As one specific example, please recall that the call operator has greater precedence, or has precedence over the operator star for indirection. And what that means is that in an expression that has both, the call operator claims all of its operands before operator star even starts to claim its operands. Okay? Normal use of precedence. But that affects how we write declarations, since declarators have the form of expressions. Therefore, similar expressions can differ in meaning if we're not careful and apply precedence. If I write star P parentheses, that tells me that P is a callable entity, because that has precedence, and that the result of the call can be dereferenced. But if I inject parentheses, now we do the parentheses first. Q is dereferenceable, and the dereferenced result is what is callable. That difference is reflected in the declarations for these entities P and Q. P, which is callable, would be declared like so. P is a function that takes arguments of a certain type and returns something that can be dereferenced to give me an int. On the other hand, in this declaration, Q is dereferenced, and that result can be called to give me a value of type int. So what we say is that here P has a function type, but Q has a pointer to function type. Although in practice, most programmers, in my experience, tend not to do multiple declarators in a single statement, the grammar of the language does allow that. And it would look like this. There is a common type to begin the declaration, and now we are declaring 4 entities. The first, a simple variable. The second, an array. The third, a pointer variable. And the fourth, a function, g. My preference, if I have to do this, is not to put them all on one line. I prefer a layout that looks like this, which I independently discovered for myself, but later discovered that it is already known as the one true comma layout. And it makes it very easy to read, at least in my opinion. And occasionally it's useful. I've discovered it's not particularly well known, but you can actually do that to declare the elements or the members of a class if they share a common type. So here we're declaring a struct named X. S, actually we're defining it by saying it has 3 members named 0, 1, and 2. I don't particularly recommend that you do it this way, but this is syntactically valid. You cannot define the function in the same place. You would have to do that outside the class, as I've shown in the bottom bullet. But nonetheless, this is syntactically valid. And it's occasionally useful. Well, there are more syntax options. Earlier, we said that a declaration starts with a type. Did not say that it has to start with a type name. It has to start with a type. For example, struct S, open, ... close braces, little s, comma, t, semicolon. This defines the type S, and as part of the same declaration, it defines variables s and t, each of type struct S. And this is syntactically valid. It's also the case that the struct can be anonymous. Here I'm declaring a variable u after having defined an anonymous struct, and this is valid. There don't seem to be many good reasons to exploit that, but that is syntactically valid. Now, there are more things that can go into a declaration that I really don't have time to discuss in this talk, but just to remind you, we can have attributes in declarations, we can have initializers of various forms, we can have qualifiers, and we can have specifiers. I believe this is not a complete list, but these are the ones that came to mind quickly. All of these things can be participants in a declaration depending on what you're declaring and what else you want that declaration to say. But the main takeaway, as we started with, is that the style that is used in expressions carries through to declarations where they become known as declarators. But that's still not the whole story, because C++ has more than C. So once we're outside the C subset, C++ had to make some adaptations. And I want to talk about 2 of them. The first is reference types. C doesn't have any. And although I've discovered it's not particularly well known, C++ doesn't have any expressions that have reference type. Now, a lot of people want to dispute that statement that I've highlighted. So let me quote to you from the C++ standard. There's the citation. If an expression initially has the type reference to t, the type is adjusted to t. So there are no expressions that have reference type. And that means that there's no operator in C++ that can produce a reference type. That means we had to adapt. And what happened? C++ adapted pointer syntax to declare an entity of reference type. Instead of the asterisk, we use ampersand or double ampersand, depending on whether you want an L value or an R value reference in your declaration. You can contrast these three examples. If you're declaring a pointer type, as you know, it's int star x. If you're declaring an L value reference type, it's now int ref y. The ampersand is where we would have put the asterisk. And if you want an R value reference type, it's int ref z in my example. But the syntax was inspired by the syntax for declaring pointer variables. So that's one. Number two, we needed one more innovation because C had no colon operator. We refer to it as the scope resolution operator. For example, if I define a struct S and I give it one data member, B, of type bool, and one member function, D, of type function taking a float and returning a double. Another way to repeat that information is to say that the data member, fully qualified S : B, has type bool, which is an object type, but the member function S : D happens to have a function type, namely double of float, which is a function type. But both B and D are members of the struct S. One happens to have a function type and the other one doesn't. So we refer to one as a member function because it has function type, and the other we refer to it as a data member. So what about pointer to member? When we declare a pointer to member, we want to indicate two things. The name of the class into which we're pointing, and the type of the member. So a declaration of a data member would look like this. I'm declaring a variable PB for pointer to B. I'm initializing it to the address of S : B, but I'm pointing to a data member because it has type bool, and it's a member of the type S, of the class S. In contrast, if I want to declare a pointer to the function, to the member function, I would do it this way. I need the parentheses because of precedence. I'm declaring a variable PD, which is a pointer to a member of S, and its type is a function type, namely function taking a float and returning a double. And I can then initialize that pointer, member pointer, to the address of S : D. So we needed to expand what C let us do because we had this new operator, the scope resolution operator. Now, this still is not the complete story for declarations, but these are some of the basic principles. I have not, for example, talked about the effect of type aliases. If you declare type defs or an alias with a using, we could discuss how they are declared and how to use them in declaring other entities. We haven't talked about reference to reference types, which are forbidden. And what you get instead is known as the reference collapsing rule. So, as others have pointed out, and I've pointed out many times in the past, no matter how much you know about C++, there's always more to learn. And with that, I'd like to draw this mini talk to a close. Thank you very much. And while we're talking about types, I'd like to talk about what I've called the universe of C++ types. It is interesting to note that the C++ language itself has a classification scheme for types. And those that are known as the primary type classifications do not overlap. They provide a partition of the universe of types. They are specified actually in two places. The core language specifies these in the subclause named basic.types, and the standard library specifies corresponding type traits in the subclause known as meta.unary. Feel free to go look. But what I'd like to discuss is largely, at least initially, is largely found in those subclauses of the C++ standard. It's a good thing that the two parts of the standard mostly agree on these. Before we look at the details, it's important to understand that whether a type is CV qualified or not does not affect the classification. Type int, the type const int, the type volatile int, the type const volatile int, those are all classified the same way. So we can ignore CV qualification as we continue. But before I get too much further, I'd like to give you a puzzle. I promise I will give you the answer at the end of this mini talk, but here is something that you may think about. As we go through the primary classifications, ask yourself for types in which classification would the following predicate be false? And please look at it very carefully. I've got some type T, and for every type T in one or more classifications, if I const qualify that type and then ask with a type trait whether the resulting type is const, the answer might be false. And the answer will be false for types in one or more classifications. So please keep that in mind as we proceed to partition the universe of types. First, we have a group of types that are collectively known as fundamental types. We have the void types, which have their own classification. And of course, there are 4 of those types, counting CV qualification. We have the std nullputter T types, and again, there are 4 of those, depending on CV qualification. And then we have the arithmetic types, which are broken down into, first, the 3 floating point types, and second, to the integral types, also known as integer types. The standard uses both. And we have much more to say about those, so let me go to the next page just to discuss the integral types. First, we have this grouping of bool and the various character types. Those are all considered integral types. In addition, we have signed integer types made up of the standard signed integer types, signed char, signed short, signed int, etc., and the extended signed integer types, which are specified as implementation defined. So your compiler may define some extended signed integer types, but I'm not aware of any compiler that does. And we have the complementary unsigned integer types, again comprised of the standard unsigned integer types and the extended unsigned integer types. And again, I'm not aware of any compiler that defines more. So all of these are considered integer or integral types. But there are more fundamental types. Oh, before I go on, a news flash. I've learned recently that earlier this year, WG14, which is the C standardization committee, made a decision to deprecate int max underscore t, which is, as you probably are aware, an alias for one of the built-in types. And the presence of that type has been one of the reasons why compiler vendors have not provided extended integer types. Because if you, for example, we got a 128-bit type, we can't officially put that in unless we change int max t to be that type. And changing int max t is, for many users, a breaking change. Nonetheless, the good news is C has decided to deprecate int max t in one of their upcoming revisions of the C standard. And that would give us at least the chance to do likewise if WG21, the C++ committee, decides to do that. They've also decided to deprecate everything that goes along with int max t. There are some macros, there are some functions, and so on. So we seem to have some resolution underway to address some of the long-standing issues associated with the extended integer types. So maybe we'll be able to get 128-bit integer types in the future. Then we have the classification known as the compound types. They're considered compound because each of them refers to one or more other types. We have, for example, arrays, which are composed of a number of objects of a single other specified type. And of course, there are two kinds of array types. Depends on whether the extent is known or unknown. We also have two reference types. In each case, reference to either an object type or a free function type or a static member function type that is specified. We have pointer types, either to void or to an object type, free function, or static member function type. We have the function types that have some number, 0 or more parameters whose type is specified, and that have a return type, which is either a void, object, or reference type. We have classes that rely on other types because they have a sequence of objects of various specified types. They also contain a set of types, enumerations, and functions for manipulating these objects, and a set of restrictions on accessing those members. We have union types, which are classes that may contain objects of different specified types at different times. We have the enumeration types, named constant values with a common underlying specified integral type. We have pointers to members that identify non-static data or function members of some specified type within objects of a class type. Okay, so those are the primary classifications, but there are other classifications as well. We sometimes talk about class types collectively intending to talk about anything declared with a class key of struct or class or union. Those are collectively known as class types. We have function object types. All pointer to function types, all class types that have an operator parens, a call operator as a member, and I've discovered this third one is not particularly well known, all class types that have a conversion function that allows conversion to either a pointer ref or ref to pointer to function type. All right, all of those are basically callables. Collectively, they're known as function object types. The important characteristic, as it turns out, is not only are these callable, but they're copyable too. That means we can use objects of these types, for example, as callbacks or in other higher order programming. The callable types are the function objects plus pointer to member types. The library considers all of those to be callable types. A few more classifications. Scalar types. Anything that's arithmetic, enumeration, pointer, pointer to member, or nullputter T type is considered a scalar type. Object types. We specify this by exclusion. Anything that's not a function type, reference type, or a void type is considered an object type. A lot of people get tripped up on reference types. No, reference types are not considered object types. We have incomplete types. So all the void types are incomplete and cannot be completed later. Any class type that's been declared but not yet defined is considered incomplete. All enumeration types in certain contexts and array types where either the bound is unknown or the element type is incomplete. Here's a little bit of code. I'm not going to discuss this in a great deal of detail, but here is a trait that I have found useful over the years. It applies some variant on what I've referred to as the detection idiom, which I coined about 6 years ago. If you do this, please use it very carefully because the answer might be different at different times in the program. If you have a forward declaration for a class, at that point, the type is incomplete. But if you later define it, it's now complete. But that's inconsistent, and that violates the one definition rule. So be very careful that you instantiate this trait at most once per type. Don't ask more than once, because you may get a different answer, and that violates the ODR. Aha! The answer to the puzzle. When you have either a reference type or a function type, you can const qualify that, but the resulting type is not a const type, no matter what the appearance says. Now, I admit that that's trivia, but it turns out to be very useful. There is a type trait in the standard library known as isFunction. And historically, that's been implemented with one primary template plus at least 48 partial specializations. Yes, 48. How do you get 48? Because you could have one of 4 CV qualifications, one of 3 reference qualifications, including none, no except true or no except false, and you can have or not have an ellipsis as an argument in the function type. Multiply those together, you get 48, and classically you need a specialization for each. And if you happen to be on a system that has non-standard calling conventions, You got to multiply by how many of those you have. All of that can go away if you know the fact at the top of this page. Here is a complete implementation. I mean, there are other ways to code this, but I think this is the clearest exposition. A type T is a function type if, when you apply const to it, it is still not const, which rules out everything except reference types or function types. So then we rule out reference types, and what's left is a function type. So there's a complete implementation of isFunction. As I say, there are other ways to code it. Here's an example how even a tiny nugget of knowledge can, in some cases, make our lives much easier. And with that, I thank you. That concludes the discussion of the classification of types in the universe of types. And in the last few minutes, I want to talk about a brilliant mathematician, Emmy Noether. She was actually a contemporary of my grandmother. They were of approximately the same age. But early in her life, her career was very difficult. Although her father was a mathematician, she was not allowed to enroll in university classes. The academic senate warned that co-ed education would overthrow all academic order. A faculty member even asked, "What will our soldiers think when they return and find that they are required to learn at the feet of a woman?" As if that would be a terrible thing. Famous mathematician David Hilbert at that university replied, and this is a famous reply, "I do not see that the candidate's gender is an argument against her admission. After all, we are a university, not a bathhouse." So finally, the Senate relented, but required that she ask permission from every faculty member whose lectures she wanted to attend. There were 2 women among approximately 1,000 students. The other wanted to study medicine and did, and Emmy Noether studied mathematics. She did win the right to matriculate. She earned a doctorate in 1907, but then couldn't get a faculty job. So she worked without pay for more than 7 years. And then she was hired by David Hilbert at the University of Göttingen, but she was not accepted by other faculty members, so she ended up giving Hilbert's lectures and still wasn't paid. Finally, she got a job in 1923 after about, 15 plus years. But then because World War II was coming, she had to flee to the US in 1933. Tragically, she died only 2 years thereafter. She, quote, produced papers and theories at a staggering rate, including a large number of rarely acknowledged contributions to works that were written by her students and colleagues. The development of abstract algebra is largely due to her in published papers, lectures, and in influence on her contemporaries. This speaks to me because abstract algebra was one of the courses I had to take as an undergraduate mathematics student. And even though I took a final exam that lasted 24 hours, nowhere in the course or in the exam was her name mentioned. And that's a travesty in my opinion. Noether's theorem devised in 1915, published in 1918, is one of the most important mathematical theorems ever proved in guiding modern physics, possibly on a par with the Pythagorean theorem. I knew Leon Lederman. He was a Nobel Prize winner. He would have been my boss, except he retired before I started at that facility. It's amazing. That theorem saved general relativity. General relativity captured the attention of physicists, but it had difficulties that even Einstein couldn't resolve. We wouldn't be celebrating this landmark theory were it not for a mathematician who couldn't even get a teaching job because of her gender. Noether's were the breakthroughs that general relativity needed to win over the physicists, but there are few people who recall her. Mathematical originality, absolute beyond comparison. She changed the face of algebra by her work. The greatest woman mathematician who has ever lived, at least on the plane of Madame Curie, at least on the plane of Madame Curie. A posthumous tribute published in the New York Times. Within the past few days, distinguished mathematician Emmy Noether died in her 53rd year. In the judgment of the most competent living mathematicians, she was the most creative, most significant creative genius thus far produced, wrote Albert Einstein. In her 53 years, many spent bucking a system. She had an extraordinary impact on algebra and physics. There's no telling what else she might have accomplished if society and fate had been more kind. So what does her work have to do with C++20? She taught us to think in terms of simple and general algebraic concepts. For Emmy Noether, relationships became amenable to generalization only after they had been reduced to general conceptual relationships. And I hope you noticed the key words here. Yes, concepts. The greatest thing in 20th century mathematics, says someone we know very well. What was her idea? That you could separate concepts from implementation. You could just deal with concepts. If anybody invented generic programming, she did. She realized that you could fully separate these two things. Her contribution needs to be remembered. And who said this? Alexander Stepanov, who developed the original standard template library, now part of the C++ standard library. So, C++20 owes concepts to Professor Dr. Emmy Noether. May she rest in peace. Let's all remember her contribution. And with that, I thank you all very much. That concludes my fourth mini talk and concludes the overall presentation called Lightning Strikes. Thank you again. I have been more than pleased to be a part of the Italian C++ conference.
Thank you very much, Walter. The talk is over. We are slightly over time, so we have no space for questions. But we have the closing note right now, so please join us with Marco Arena and everyone else.
All right.
Thank you.
Bye-bye.
Thank you. Bye.